Alright, hello, problem one. So as always, there's several ways to solve one of these problems. This is one that actually has a really fast and easy solution if you are familiar with the right technique. So you have to know a bit about even and odd functions for this one, right? Optionally. Remember that even functions are ones where plugging in a negative number is totally the same thing as just plugging in the positive number. So like a function where plugging in 5 is totally the same thing as plugging in -5. You know, they both turn out to be 7, for example. These functions look like this, right? They are totally symmetric about the y-axis, right? They have to be that way because plugging in a negative one has to be exactly the same as plugging in a positive one. So they have to be symmetric left to right like that. Odd functions are ones like where plugging in a negative number gets you almost the same thing as plugging in a positive number, but it's the negative of that. So instead of looking like those green ones do up there, they're going to look more like these blue ones where they do something over here, but then they do something else over here. But not just anything else, the exact opposite of what was happening on the other side. So whatever you get when you plug in -2, you get the same thing when you plug in +2, but negative, right? These y values are the same as each other, but negative is my point. And so consequently, the whole graph is like that. Then it must be symmetric in a different way. Not symmetric like this, but symmetric like this, right? Man, that flashing is really not great. I have to work on that. But yeah, so it looks like that. And so the point is, when you do the integral, the areas on the left and on the right are going to be opposites of each other, right? So I actually have this one pulled up here. Oops, hold on. Yeah, so the point is this is an odd function, right? And there's a couple ways to be aware of that. One thing you need to know is that cosine is an even function, right? Cosine is an even function. You can know that either lots of ways to know that. You can know that from the graph, for example, right? I know that the graph of cosine actually looks like this, right? It is symmetric about the y-axis, so that's an even function. So plugging in negative numbers is the same as plugging in positive numbers for cosine, right? So that means then that all of what we have here, this is a odd function, right? It's an odd power of x, so that's an odd function. This is an odd function inside of an even function, and then those are multiplied together. So if you know the rules of multiplying and composing even and odd functions, you can work out that that's got to be odd. Or you can work it out for yourself right now. You can say, well, what's going to happen if I plug in a negative number into here? Well, I can see that out here, that's an odd power, so it's going to work out in the odd way where the negative just comes out. Same thing going on in here. This is an odd power or an odd function, so the negative is just going to come out like that. But then on the inside, right, this cosine, remember, is an even function, so that negative just disappears. And so what we end up with when we plug in a negative number into this function, notice we get the same exact function, but with a negative, right? So that's exactly what it means to be an odd function, right? We don't get the exact same thing, we get the negative of the exact same thing. And that's what it is to be an odd function. And so what that means is that what this function is doing on the left-hand side and the right-hand side are exact opposites of each other. So I actually have it pulled up here. If I can find it. Here it is. Oh, hang on. Wait. Aha. Yeah, so here it is. This is the same function, x to the 5 cosine of x cubed. And notice that what it's doing on the left side and the right side are totally the same. And so that means that the total area that we're interested in, from -1 to +1, is 0, right? And you can see it telling us that right here. It is 0 because the negative red area from -1 to 0 and the positive green area from 0 to 1 cancel each other out, right? It's always like that for all odd functions. So if I'm doing one of these problems and I see that the function is odd and I see that the bounds are symmetric, like same thing on either side of 0, like say -1 to 1 or -7 to 7, then I know immediately that's got to be 0. And I don't need to do any calculations or any whatever. So one possible answer to this problem was to just say the function is odd, so therefore it's 0. Boom. Easy peasy. Right? Function is odd and the domain is symmetric. The bounds are symmetric. So therefore it's got to be 0. No calculus, no nothing required more than that. So great. So that's one way you can do it. Now let's say though that you didn't know about even and odd stuff. You don't know about that. You can do it directly with calculus. Right? So let's talk about that too. So on first glance, you may be tempted to try some integration by parts because after all, it is the product of two things. It is the product of two things. But what two things? Well, this second thing is kind of ugly. I don't like it. I don't like how it has an x cubed on the inside because if I have to work with this with integration by parts, I'm either going to have to take the derivative of that, which is going to give me a 3x squared on the outside, and that's going to be a whole weird thing to deal with. Or worse, I might have to take the integral, and I don't even know how to do that because of the chain rule, right? We discussed that earlier. So that's not the move. Don't do that. The move is instead to immediately make a substitution to change it from cosine of something cubed to something more normal, just cosine of something. So so let's make that substitution real quick. I'd normally go with u, but I'm about to use that letter in a minute, so I'm going to call it something else for now. So I'll call it w. So that will be my new variable. This thing here is now cosine of w instead of cosine of x cubed. And then the dx, right? Well, I am going to need a 3x squared, or at least I need an x squared. I guess I can put the 1/3 over here. Some people like to think of it that way. But I am at least going to need an x squared. Or actually, some people like to think of it as putting the whole thing on the other side too. Like that. That's fine. Personally, I find that kind of confusing. Honestly, I just like to leave it like that. And then just think like, okay, so I need a 3x squared. So I need to collect a 3 and 2 x's to become my dw. So where am I going to get those from? Well, I've got 5 x's over here. So I can at least take 2 of them and put them over there, and that'll be the same thing. But then what am I going to do about that 3? I can't just randomly add a 3. But actually you can. As long as you randomly add a 1/3 at the same time, you can totally randomly add a 3. Right? So yeah, so that's how I like to think of it, is just kind of do it like that. And so now that we've done that, now we're good to go on the substitution because this x cubed on the inside is now a w. Here we have exactly an x cubed, which is another w. And then here we have our dw. So this is looking great. This is the very nice 1/3 integral of w cosine of w dw. Now we did make a substitution here. We might have to think about the bounds of the integral. Right? Our original bounds were in x. But now we have translated our integral from this old one in x to this new one in w. So our bounds we should really take with us. Is one option, right? The other option is to convert back to x in the end. That's totally valid too. But if we take our bounds with us, right, it's actually super easy because it turns out, you know, if you plug those bounds in for x, right, 1 cubed is 1, and negative 1 cubed is negative 1. So actually, the new bounds, even in w, are still negative 1 to 1. So that's super convenient. Gotta love that. The only difference is now we've got this extra factor of 1/3. But that's fine. Okay. So unfortunately, though, what we're looking with still is not immediately recognizable as the antiderivative of something. So we're still going to have to do some technique. And now I think integration by parts is going to be the move, right? Because you can see it's the sum function times another function. If we swap one for its derivative, I bet you if we swapped this one for its derivative and swapped this one for its antiderivative, we would be in good shape because that would just be sine, and that's super easy. Right, so let's do that. So I'll use the formula and color scheme from up here. Let me actually snag it real quick. Oh, that's right, I never switched back to this, damn. There. Right, so there it is. So what I'm suggesting is we let w be u, because that's the thing that we'll be replacing with its derivative. That would just be 1, right? You don't even have to write that. So that's a good exchange, I'd say, right? You take a variable and then it's gone, so that's helpful. And then the other one, right? If this is the cosine, whoops, we're replacing that with its antiderivative, which is just sine. So that's wonderful. So that's definitely the move, right? If we replace, you know, w cosine of w with just sine of w dw, that's the move. That's totally the move. So let's do it. So according to the formula, right, this integral here of u dv, whoops, this is u and this is dv, right? That's this here. According to the formula, we can replace that with u times v. So u times v. Are you kidding me? Are you kidding me? Didn't I? Why is that not do not disturb? I don't understand. Okay, so minus the integral of v du. So v du would be sine of w dw, right? So that's v du, sine of w dw. And that's great because that's super easy. That's integral of sine is negative cosine, right? So since this already has a minus sign, that's going to be positive cosine. Now, by the way, some people get kind of concerned about like the bounds for integration by parts. Yeah, technically I should be saying the bounds there or whatever. Honestly, pro tip, don't worry about that level of detail on the notation. It's not worth your time. Just sort of zoom out, just do the whole integral first. Don't worry about that stuff. And then once you've got the integral, boom, then plug in your bounds. It's just much easier that way, in my opinion. So yeah. Okay, so here we go. So now we're good to plug in the bounds. Let's do it. So plugging in 1, that's 1 times the sine of 1 plus the cosine of 1 minus negative 1 times the sine of negative 1 plus the cosine of negative 1. Okay? So yeah. So first of all, what is the sine and cosine of 1? Well, on the unit circle, you know, you learned about all these like important values like, you know, pi over 2, right? Where there the sine and cosine are like really really nice, important values, you know? Or even this one, like pi over 4, right? This angle being pi over 4, this distance along the edge of the circle being pi over 4. But if you go a distance of 1 along the edge of the circle, or you literally 1 radian, that only takes you to like here or so. And the actual values there are not very nice values. In fact, damn, I was gonna look for what it was for a second, but I actually can't find it. So can't find my phone. I mean, so let me look it up real quick. It turns out that the sine of 1 is 0.84. It's irrational. And the cosine of 1 is similarly not very nice. And it's not like other irrational values where it's like, you know, square root of 2 over 2 or something, or you know, some nice, like, irrational but very nice algebraic description of the number. No, it's not like that. These numbers are not the square root of anything. They're not the square root or the cube root or the square root minus the reciprocal of the whatever. None of that. There's no nice description of these numbers. They're transcendental. Which is a very flattering way of saying very ugly. So yeah. So anyway, that's a bit of a tangent. The point is, sine and cosine of 1 are not nice numbers. They're these ugly irrationals. But that's okay. So we can actually use our knowledge of, well, I should say, kind of losing my train of thought here. Let me be careful. This is the correct answer. Some of you got to here and stopped. You didn't simplify it any further. That's fine. This is close enough to correct. I gave you full points if you got here. But there is a, as we know from the other argument about even and oddness, we know that this is actually 0. So you can simplify this a lot, right? Let's use the even and odd facts, right? We know that cosine and sine are even and odd functions, right? So that means cosine of a negative number like this is the same as just the positive number like that. So cosine of -1 and cosine of +1 are actually the same, because cosine is an even function. It's symmetrical around the y-axis. Plugging in negative numbers and plugging in positive numbers are the same thing, right? All equivalent to saying it's an even function. Finally, sine is an odd function, which means plugging in -1 is the negative of plugging in +1, right? So I know it's like that. So that's important because that allows me to simplify this expression. Right, we have the sine of 1, the cosine of 1. Now I'll distribute in that negative, so let's actually distribute in. So this is plus sine of -1 minus cosine of -1. Okay? All right, so now let's work on this. Actually, I won't do it like that. So the sine of -1, right? We know that that's the negative sine of 1. And then the cosine of -1, we know that that's actually the positive cosine of 1. So I hope, so I maybe didn't make that super clear, right? This was, these are what they are. But then this one's now negative. It was minus. It was plus, but now it's minus because it's odd. And then this one was minus, and it's still minus because it's even, right? So, in other words, this one got its sign flipped because it's an odd function, but this one kept its sign the same, which was already negative because it's an even function. And so you can see that what ends up happening is those cancel each other out, and so do those, and it turns out to be 0. So there you go. So if you do it the long way, you can work it out on a calculator too if you don't know the even and odd stuff. It turns out to be 0, even if you do it the long way. So yeah, that was how to solve this problem. So a lot of people were at this point and they said, product of two things. Let's try and use integration by parts. That makes sense. but unfortunately you're going to run into problems with that x cubed being on the inside. So definitely a substitution to get rid of that first is the move. Alright, I think that's about all I have to say about that one. Thanks for watching. Let's go for the next one.